So, having said down here that we're thinking of sine theta, we can think of sine theta or cos theta or tan theta as just representing a number. There are certain properties of these numbers that allow us to do some extra things that you can do with these numbers that you can't do with other numbers. Okay? We saw with logs, for example, we had some identities there. The log of x plus the log of y is the log of x times y and so forth. They're things you can do with the log numbers. I'm going to have a look now at the things you can do with these trig numbers. And it goes under the fancy name of trig identities, sitting in here. I might leave that one on top. So, amongst these numbers, there's lots and lots and lots. I said many, that should be heaps. Okay? Trigonometric identities, you could probably be from here to Christmas and you still couldn't write down all the identities that hold. Okay? So, there are lots of them, but I'm just going to single out a few for you that you probably should know. So, these are the first three ones, first three trig identities that you should be familiar with. And let me try to convince you that they are reasonable. So these things are true no matter what value theta takes, is the idea of these. So let me call them 1, 2 and 3. And let's say, right, number 1, if I were to draw a right-angled triangle, and if I were to put theta as one of the sides in there, then we know, I think we were calling these A, B and C, we know that because the angle sum is 180 degrees, we know that this angle here is 90 minus theta. Now let me label the sides A, B and C as we did before. And on the left-hand side of this identity it says sine theta. So in my picture here you can see that sine theta will be the ratio of the opposite side to the hypotenuse. And the opposite will be A, the hypotenuse is C, so sine theta would take the value A on C in that triangle. On the right-hand side, I have cos of 90 minus theta. Now, 90 minus theta we know is the angle B, and when I'm at angle B, the cosine is the adjacent over the hypotenuse, and for this angle, A is the adjacent side, and C is still the hypotenuse. So you can see that the cos of 90 degrees is also A over C, and so therefore must be sine theta. And so the cos of 90 minus theta must be the same as sine theta. And that's true no matter what value of theta you choose. And of course, if we were to go back and have a look here in our box, the sine of 30 is equal to the cos of 60, 60 being 90 minus 30. Likewise, the sine of 45, 90 minus 45 is 45. They're the same. And cos of 30, let's go sine 60, 90 minus 60 is 30, so the cos of 30 must equal the sine of 60. And so we can see verification of it sitting there, but it's true not just for 60, 45, 30, it's true for any of value of theta sitting in there. So that means if I see the number sine theta somewhere in my expression, I can replace it by cos 90 minus theta. Why I would want to do that just for the minute I can't tell you, but I can if I want to. All right? So there's an operation that I'm now allowed to do in an expression that involves trig functions that I couldn't do if it involved log functions, for example. Okay, so this is trig-specific manipulations that I'm not allowed to do. Let's have a look at 2, which says tan theta is sine theta divided by cos theta. Let's stick with this triangle that I've got here and have a look. Tan theta, we said, was the opposite over the adjacent. So tan theta is A on B. Let me also work out sine theta and cos theta. Sine theta would be the opposite over the hypotenuse, and the cosine of theta would be the adjacent over the hypotenuse. And for theta, the adjacent is B, so cos of theta is B over C. So I have tan theta is A over B. Let's have a look at sine theta divided by cos theta. And you can see that that is A over C divided by B over C. You know that when you divide by a fraction, that's equivalent to multiplying by its reciprocal. So that's A divided by C multiplied by C over B. And you can see that that is A over B, i.e. tan theta. And were I looking for verification of that, go back to our table. The tan of 45 is sine 45 divided by cos 45. 1 on root 2 divided by 1 on root 2 is indeed 1. Tan of 60, sine 60 divided by cos 60. I've got the square root of 3 on 2 divided by a half. That's just the square root of 3. And so on. So again, you can see verification of that identity sitting in our box there. And the last one, 3. Well, I've got values of sine and cos here. So let me just point out. Sine squared theta, and this is just to confuse you. Again, it's a quirk of the history of mathematics that we're now using this squared symbol here, and we actually mean squared there. Whereas if I put -1 there, I don't mean -1, I mean inverse. Okay, so unfortunately that's how the notation has grown up, and we have to learn to live with it. So sine squared theta is actually the same as sine theta, all squared, which is of course just sine theta times sine theta. And likewise with cos squared. So this notation works for everything except -1. Okay. Yeah, I know. I would change it if the world would let me, but it won't. Okay. So here we go. So sine squared theta plus cos squared theta, according to this, should be A on C all squared plus B on C all squared, because that's sine theta and cos theta. Now, these fractions have a common denominator of C squared. I suppose, let me write it in. It's A squared on C squared plus B squared on C squared. So that's A squared plus B squared on C squared. But we know that A squared plus B squared is equal to C squared, because this is a right angle triangle, and that is Pythagoras' theorem. That's Pythagoras says that. And so if A squared plus B squared is equal to C squared, that's C squared on C squared, which is 1. So sine squared theta plus cos squared theta will always be 1, no matter what value of theta you have. And so if I see sine squared theta plus cos squared theta in any expression, I will probably want to write it just as 1, because that's going to look simpler. So there's a nice algebraic manipulation I can do with these numbers. And again, I guess we should look back here. Let's square sine squared 30 plus cos squared 30. A half squared is a quarter. Root 3 on 2 squared is 3 on 4. So 1 quarter plus 3 quarters, 1. And so on. Okay, so it always works. So for those identities, it was relatively easy for me to convince you I think you're convinced, are you not, that they're true. For the next three, the convincing is not so easy. So much so that I'm going to skip it. Okay? I'm going to say, trust me on these ones. So these are some more trig identities. These are called the addition formula because it says the sign of alpha plus beta, and it gives you a formula for which it's actually true. So let me highlight those. And I wouldn't expect you to memorise them, but I guess if you were clever, you'd probably have it written somewhere. I guess. So for example, if I just quickly just do an example of this. If I had alpha was 15 degrees and beta was 30 degrees, then if I work with the first one, it would say the sine of alpha plus beta is the sine of 15 plus 30, which would be the sine of 45 degrees, which if I have a look on my table that I keep needing to bring to the top, here it is. The sine of 45 degrees is 1 on root 2. So in here, on the left-hand side, I get 1 on root 2, and that will be 0.7071 or thereabouts to 4 decimal places. On the right-hand side, I need to work out these quantities, so let me do it. So I'll go sine 15 cos 30, and do that on your calculator. Put sine 15 times the cos of 30. I mean, you don't have to, but that's what you would do. And you're going to get something like 0.2241 to 4 decimal places. Then the next thing I have to work out is sine 30 cos 15. So sine 30 cos 15, and when I worked that out, I got something like 0.4830, accurate to 4 decimal places. And so on the right-hand side I have sine alpha cos beta plus sine beta cos alpha turns out to be approximately 0.2241 plus 0.4830, and that comes out nicely to be 0.7071. You get the same result. And so what that says is if you want to, you can rewrite this number as that number, or vice versa. You can write this number as that number. And you might think to yourself, would I ever want to do that? And the answer is, we will see situations where, yes, you do want to do that. Now, given these trig identities and the ones we had before, we can derive lots of others. I can say, so given some identities, we can derive lots more. We can derive lots more. And so I'll just give you a kind of indication of what you can do. As I say, you could be here from till Christmas and you still won't have derived all the possible trig identities. But so I'll say here, for example, if I choose alpha equal to theta and beta equal to theta, and we tend to use Greek letters here. Do you know your Greek alphabet well? You'll get better at it. We've got 3 letters in here anyway. We've got alpha, beta and theta so far. Anyway, if I choose that, then from which one will I choose? I might choose this one. If I go to the cos alpha plus beta, on the left-hand side I have cos of theta plus theta must be, and on the right-hand side it says I can write that as cos theta minus sine theta sine theta. So in other words, I can say, look, the cos of 2 theta is cos squared theta minus sine squared theta. And there is another trig identity. So, if needs be, I can replace this number by that, or vice versa, in any expression. Let's do one more. So another example. Now, we had before that sine squared theta plus cos squared theta is equal to 1. If I rearrange that, I could say, look, I can write cos squared theta as 1 minus sine squared theta. So you can see what I'm doing here, in that I am now thinking of this whole thing here as just being a number. And so therefore I can subtract it from both sides. Okay, so I'm doing algebra here with these trig ratios. Now, that expression I'm going to put into here. So let me label that number 1. So I'll say put this in equation 1, and I will have cos 2 theta is, now cos squared theta I can rewrite as 1 minus sine squared theta. So this becomes 1 minus sine squared theta minus sine squared theta, which, if I collect like terms, because these numbers are the same number, I have here cos 2 theta is equal to 1 minus sine theta minus sine squared theta, so that's 2 sine squared theta. And there is another trig identity. And as I say, I can keep going for ages and derive lots of these things. The important thing for you, I would say, is those three there. The first ones I gave you, they're the most important ones. As you get more down the track in your mathematical development, these ones will become very important. Okay, so the two boxed ones that I've given are the ones that you will use the most, I would say.